So now we're going to consider copying bits and whether we can copy qubits or not. And so let's look at the classical bit case first. Um, so if we write the CNOT gate but apply it to just classical bits rather than qubits, we can see that gives us a circuit that will allow us to essentially copy, so duplicated input bits, and then have, so if we have our CNOT gates, and so we initialize one input, so the top input to X, which is going to be the bit that we want to copy, and then we just initialize the other input to 0, regardless of what we want to copy, so this is sort of a scratchpad space. So we look and see what happens. If X is 0, nothing happens in this control here. We just end up with two zeros, because essentially we have another copy of X. If X is 1, it activates the XOR gate, so then 0 is XORed with 1, and so our output is going to be two ones. Okay, so essentially we've copied whatever the input of X was in the first wire into the second wire without doing anything to what was carried in that first wire. Okay. All right. And it really shouldn't be at all surprising that we can do this, right? Because we know with our experience using computational devices that yes, you can easily copy classical information. All right. So now the question is, so does the CNOT gate copy qubits? Okay. So the idea then would be, if my input is going to be x0, is my output going to be xx? But to answer that, we really got to say what we mean by x0 and xx here. And so for that, we're going to use the notion of tensor products. Okay, so if psi is an arbitrary single qubit state, okay, so a0 plus b1, and phi is also an arbitrary single qubit state, c0 plus d1. Then we'll define the tensor product of those two states, okay, which we can write as psi, so this kind of x with a circle around it, tensor phi, or you'll sometimes write it just by juxtaposing those two qubit states. But essentially, so by definition, this is going to be the result if you just sort of multiply this out. Okay, so just using ordinary distributive laws, collecting and multiplying any scalars that you encounter, and so then when you encounter something that's like 0 tensor 0, then that becomes just the standard computational basis vector 0, 0. Okay, all right, so if I just sort of multiply everything out here, then the result will be AC 0, 0 plus AD 0, 1 plus BC 1, 0 plus BD 1, 1. Okay. All right, so now to answer this question, so does CNOT copy qubits? Then the question is, so if we input, okay, so psi tensor 0 into CNOT. Okay, so again, this is kind of the qubit I want to copy, and there's my scratch space. Is the output going to be psi tensored with itself? Okay. All right, so that's a very simple question to answer now, because we can easily calculate each of these things. Okay, so psi tensor with 0 is what? So A0 plus B1 tensor with 0, which is A0, 0 plus B1, 0. Okay. All right. And what if we apply CNOT to this? Okay, well, remember, and all gates are linear. Okay, so I can just kind of distribute here. We know CNOT does nothing to 0, 0, but 1, 0, it flips to 1, 1. Okay, so this will be A0, 0 plus B 1, 1. Okay. All right, now the question is that the same thing as psi tensored with itself? But it should be pretty clear to see that it's not, right? Because essentially the idea is I'm going to get some of these cross terms over here when I do this. Right, so psi tensor with itself is going to be A00 plus AB 01 plus AB 10 plus B squared 1, 1. Okay. Right. And so in general, these two things are not equal to each other. Right, so that means that right, C-naught gate kind of has a different interpretation in the classical case that we can't impose on it in the quantum case, right? So it's not just copying information from the first qubit of the system onto the second qubit of the system when we input psi tensor 0. Okay. All right, so then next we'll try to answer the question, well, C-naught gate doesn't just copy an arbitrary qubit. Is there some circuit we can come up with that would copy an arbitrary qubit?